Hey math fans, Alex here to you today with a problem from the 1995 Putnam Exam. It says to evaluate the following. Okay, so I consider this what's called a continued fraction, or sometimes a nested infinite fraction. It's the eighth root of a number minus 1 over a number, minus 1 over a number, minus etc., etc. And we essentially have to express that answer in the form a plus b times root c all over d, where a, b, c, and d are integers. Okay, so the first thing that I'm going to do to get started is I'm going to go ahead and call this thing x. And if you want to be absolutely rigorous, I suppose you should show that x even exists. But the problem does say to go ahead and evaluate it. So there's kind of that implicit assumption that it does exist. So then the natural thing to do would be to take the eighth root of both sides. Okay, so then we have that x to the eighth power is equal to 2207 minus 1 over 2207 minus 1 over 2207 minus etc., etc. Okay. And as I mentioned before, this is in the form number minus 1 over number minus 1 over number, and this kind of recursion relation is going to be useful for us. Because if you notice, the denominator of this first fraction right here, isn't that also the exact same thing as number minus 1 over number minus etc.? Okay, so what we can say in the way that you usually solve most problems is to note that this thing is also x to the eighth. And since it is also x to the eighth, we can really go ahead and write this expression as x to the eighth is equal to 2207 minus 1 over x to the eighth. The next thing we're going to do is we're going to turn this into a polynomial. So we're going to go ahead and multiply both sides by x to the eighth, where x, of course, isn't equal to 0. And what we get is that x to the 16th, and then I'm going to move this over, minus 2207 x to the 8, and then this is going to turn into a minus 1, which when we move it over is going to be a plus 1, and that equals 0. Alrighty, so all we have to do is solve a 16th degree polynomial. Who's with me? Yeah, that doesn't sound too convincing. Well, remember, how does this game go? Well, notice that this is x to the 16th, and this is x to the 8th, which is a multiple of 16. So remember what you did when you had problems like x to the 4th, I don't know, minus 6y squared plus a constant equals 0. Sorry, not y, but x. What you did was you considered this expression quadratic in x squared, right? Because this thing is nothing but x squared squared minus 6x squared, which is the linear term, plus 10 equals 0. And then you use the quad formula to get the x squared was equal to, minus b plus or minus, etc., etc. And then you just took a square root. So we're going to do something very similar to that, just a couple of different times. And the more that we work on this problem, the more we discover that it's not as bad as you think it is. Okay? So let's go ahead and get started by writing this as, let's go ahead and define y to be the same thing as, okay, so the first thing that I'm going to do is I'm going to go ahead and define x to the 8th as y, so then this turns into a quadratic expression. Okay, so now what we're going to have is y squared minus 2207y plus 1 equals 0. Okay, and then using the quad form, we get that this is equal to y equals negative b plus or minus the square root of b squared, but since it's negative and you're squaring it, I really don't have to include the negative. It's positive regardless. Minus 4ac all over 2a. Okay? So Again, I assume the people on the Putnam exam don't have access to calculators, so we have to evaluate this radicand right here. Also, the plus and minus, I'm going to go ahead and leave the plus or minus out and put it at the very end. That's just a personal preference. I don't feel like writing it each time, but we'll see in the end that there are actually 4 solutions, but 2 of them don't exist. So we're actually going to have 2 solutions, a plus and a minus. Okay, but now what we need to do is we need to focus on this radicand and figure out what 2207 minus 4 is. Well, I note that I can write this as a difference of squares conveniently. I can write this as 2207 squared minus 2 squared, okay, which is equal to 2207 minus 2 times 2207 plus 2. Now, ideally, since these are both under a radical, we want to look for perfect squares that go into both of these. Well, I know that 2205 certainly isn't prime because I could factor a 5 out. And when I do that, I get that this is 5 times 441, which is a perfect square. Okay. Now, what is 2209? Well, 2209, I don't know what that is per se, but I do know that it's between 40 squared, which is 1600, and 50 squared, which is 2500. So it's somewhere between there. And if it were a perfect square, it would have to either end in 3 or 7, because 3 squared and 7 squared both end in this 9. Okay, so the only options are 43 and 47. Okay, but I'm going to stick with the one closer to 50. So I'm going to go ahead and guess that this is 47 squared. Okay, and a quick computation will point out that I'm right. This is actually 2209. Okay. So now that I realize that that's 47, that makes our job a little bit easier, because if this is 47 squared, 441, well, that's 21 squared. That one I actually do know. Which means that I can replace the stuff under the radical, or better yet, I can just simplify the radical as follows. So this is going to be y is equal to, I'm going to write this as maybe 1/2 times 2207 plus, and then I'll have a 21 times 47 root 5. Okay. But remember, we substituted in that y was equal to x to the 8th. Okay, so this is really the same as x to the 8th. And there you go, you have a closed form expression for x to the 8th. The natural thing to do now would be to take the square root of both sides. Okay. Let's just mess around with what this is. So on the left-hand side, this is going to be x to the 4th. And on the right-hand side, we have, 1 over root 2 times this square root, 2207 plus 21 times 47 root 5. But then what I'm going to do is I'm going to go ahead and rationalize the denominator. Okay, and the reason that I want to do that is I don't want this to be divided by a radical. Okay, because remember the overall solution was a plus b root c, where c is probably 5, all divided by d, where those are integers. Okay, so let's just rationalize, multiply this by root 2 over root 2, and we get something a little surprising. We get that this is x to the 4th equals, now it's just 1/2 times the square root of, now this square root of 2, this is going to come in this radical, so I need to multiply both of these guys by 2. So I'm just going to go and do that. So this is going to be 2 times 2207 plus 2 times 21 times 47 root 5. Okay, so our job is to try to simplify this to write it in a form that possibly looks like a plus b root c, where c is probably 5, all divided by d. And the thing to note is that since this is clearly possible, okay, the solution actually does exist, x to the 8, you can't actually evaluate that square root, you can go ahead and assume that a number like this is actually going to go ahead and be in the form, okay, so this radical of number plus number root 5, we're going to go ahead and say this can be written as sum a plus b root 5. Now, in general, someone pointed out in YouTube comments, I made this video before, and someone pointed out, thankfully, that this is not always true. I stated it incorrectly as a fact, and there are certain conditions that have to be followed. However, again, since the solution exists, and we're taking the square root, and it has to be written in a certain form, we can go ahead and assume that the square root of number plus number root 5 is another number plus another number root 5. Since this is a competition style question, I would go with your gut. Okay, so let's figure out what that would have to be. Let's just see. Okay, so we have that the square root 2 times 2207 plus 2 times 21 times 47 root 5. We're going to see if that equals a number like a plus b root 5. Okay, so what do? We square both sides. Okay, we square both sides, and what we're going to end up with is 2 times 2207 plus 2 times 21 times 47 root 5 is going to equal, when you FOIL this out, you're going to have a non-root 5 term, which is a squared plus 5b squared, and you're going to have a root 5 term, which is 2ab root 5. Okay. Now, in order for these numbers to equal each other, we must have that the non-root 5 part of the number equals the non-root 5 part of this number, which means that we have to have 2 times 2207 equal a squared plus 5b squared. And also we have to have that the root 5 part of the number has to equal the root 5 part of this number. So we have to have that 2 times 21 times 47 must equal 2ab. Now you might see why I left the 2's there. Maybe you were wondering about that. Okay, because this system has to have a solution where a and b are both integers. So we can go ahead and cancel out the 2's on both sides. And look at that. We are gift-horsed a product of two integers, 21 and 47. Now, is that the only possible product of those numbers? No, because 21 is equal to 7 times 3. Okay, so if you break everything down into primes, because 47 is prime, we would have that this is actually 7 times 3 times 47, which means there are 3 different products. But before I state those products, let's look at this equation for a second. Let's see if we can establish an upper bound for, say, a. If I cross this term out, and noting that this is about, we can say that this is roughly what? 4,500-ish. A can be at most 7. A has to be less than 70. Because a squared would be 4,900, and clearly this is less than 4,900. So the bigger of the two, and b has to be smaller, by the way, since we're multiplying it by 5. So the bigger of the two numbers has to be less than 70, which clearly holds in this case. However, if you break it up any other way, that isn't true. Okay, so for example, if you decide to take 7 times 47 and let that be your A, that's bigger than 70. And if you decide to take 47 times 3 as your A, that's also bigger than 70. Okay, so the only combination that works was the one that we just happened to lay out right here. So from here, we can immediately just go ahead and say that the solution to the system is A equals the bigger of the numbers and B equals the smaller of the numbers. And since that's the only one that could solve the bottom equation with the constraints at the top, that is the solution. Okay, so what we have is, to go back up here, we have now that x to the fourth is equal to 1/2 times a plus b root 5, where a is 47 and b is 21. Now you might think to yourself, oh, that was a lot of work. I don't want to have to do that 2 more times, because we have to square root this twice more. But this is going to be the same story, right? All of this was basically just setting the ground so that we don't have to do this again. We're going to also assume that the square root of this can be written as, some other, c plus d root 5, and go onward from there. So I'll do this just to kind of show it. But what we're going to have here is, again, x squared is equal to 1/2, because that square root of 2, when you rationalize it, is going to come into the square root, and we're going to have 2 times 47 plus 2 times 21 root 5. Again, we're going to have to solve a system of the form. I'm not even going to write it and show that work, but we're going to, again, have something like 2 times 47 equals, should be a prime, but who cares? And then 21 equals AB. Well, that's even easier to solve. There's only one possible combination of positive integers whose product is 21. Well, that's not true. There's 1 and 21, right? But again, A has to be the bigger of the two, and 21 squared is much bigger than this number. Okay, so the only possibility is that A is equal to 7, right? A has to be the bigger number, 7, and B is 3. It's the only way we could break up this product and have it satisfy the constraints of the first equation. And again, we're assuming the solution exists, so we can constantly take square roots and assume that that's equal to a plus b root 5. Can't assume that in general, though. But at this point, we can go ahead and replace this radical. And we can say that x squared is now equal to 1/2 7 plus 3 root 5. We're almost done. We just have to take one more square root. And we get that x is equal to 1/2 times square root of 2 times 7 plus 2 times 3 root 5. And one more time, we're going to have the following system to solve. Worst brace ever. Okay, so we're going to have the following system. 2 times 7 equals a squared plus 5b squared, which at this point we shouldn't even need to write, because then we have 3 equals ab. And since 3 is prime, the solution immediately is a equals the bigger number 3, b equals the smaller number 1. And then we can go ahead and write that x is equal to 1/2 times a plus b root 5. All right, so the solution x that we can write in the form number plus number root 5, all divided by another number, where those numbers are integers. And the last thing that I'll do to finish this solution before I make some remarks is note that in the beginning, I said as a personal preference, I didn't feel like writing plus or minus, okay? But really there is a plus or a minus when you repeat the argument. So I'll go ahead and put that minus right here, and that is our solution. Now, one remark that I'll make, okay, again, because I did think about this. So, assuming that a and b are integers, we have that a plus b root p, where p is a prime. This is what we call a field. And a field has a bunch of super nice properties, many of which you studied in grade school. commutativity, associativity, distributive law, inverses, all that kind of stuff. But you can't take this, it's not closed under square roots. Fields in general are not closed under square roots. For example, the rationals, that is also a field, okay, but it is not closed under square roots. So if you take the square root of a rational number, you maybe aren't going to get a rational. Of course, there are exceptions, like 0. Square root of 0 is a rational, but that's not generally the case. And in general, when you take the square root of something like this, it's not a field. However, there is a subclass of fields called quadratic fields. Okay, and these quadratic fields, which are very small in number, quadratic fields are closed under square roots. Okay, so this is not a quadratic field, but I will give you a really cool example of a quadratic field. The complex numbers, which are the numbers of the form a plus b times the square root of -1, or a plus bi, this is a quadratic field. Which means that if you have some complex number z, the square root of z, you can write that in the form a plus bi. So that's just a really cool property of the complex numbers. And anyway, I hope that was helpful. Have a great rest of your day.